Lecture number 7, entitled The Selection of Phases, Poles, Stator, and Rotor Slots for selection for use in designing 3 types of electrical machines. The selection number phases, of course, is always the first decision, and it's not a big decision. It's usually 3 phases. Most inverter-fed machines that are used around the world today are 3-phase motors, particularly grid motors. Because of that, IGBT manufacturers and MOSFET manufacturers are transistor people. They package their transistor bridges in sets of 6 for 3-phase drives. It's not uncommon to use 2 3-phase circuits and 2 bridges, or even 3 bridges and 3-phase circuits in a machine. It's useful for fault. This is useful for fault tolerance, and it's also useful for reducing the cost of the electronics, or there's some other benefits of using multiple bridges. Large machines, like generators used in power plants, frequently use more than one 3-phase circuit. Stepping motors use 2, 3, and 4. There are even 5-phase step motors. Switch reluctance machines use 2, 3, 4, 5, and 6-phase stators. The 2-phase stator is a very popular one for vacuum cleaners and fans and things of that sort. Very famous vacuum cleaner uses a 2-phase switch reluctance motor that goes 100,000 RPM. But these lectures are all based on stators that use 3 phases or multiples of 3 phases. Some of this is repeated from the last slide, but there's more details on this one. Now, for permanent magnet generators, it's not uncommon to have a single phase or a 2-phase. It's not necessary to have a 3-phase if you're going to rectify the output anyway and use capacitors to smooth out the variation in the voltage to make it a smooth DC. One of the advantages of increasing the number of poles is you improve the torque density. We'll show that in a subsequent slide. But the downside of increasing the number of poles is that the iron losses in the yokes and teeth goes up because of the increased frequency. And also, with the increased number of poles, the transistor losses will increase. But in terms of torque density, it's better to have a high number of poles. The relationship of the number of slots to the number of poles is another story entirely. There's 2 types of combinations. There's the integral slot windings. That's where the number of poles divides evenly into the number of stator slots with no remainder. Fractional slot winding is where the number of rotor poles does not divide equally into the number of stator slots, so there's a remainder. But these are called fractional slot combinations, and one of the advantages of those is that they yield lower cogging torques if it's a permanent magnet motor. The ratio of the slots to pole numbers determines the winding choice options for all 3 of the motor types that we're talking about here that use the same stator. Sometimes with certain designs, one of the most important elements in the whole design is to make the end turns short. If you must use a radial flux motor and you have very minimum axial space to put it in, you've got to keep these end turns low. So your best choice in that case is to use a fractional slot winding, a pole and slot combination where the coils are wrapped around a single tooth so that the end turns are real short. But having said all those things, to have balanced 3-phase windings or 6-phase or any windings as far as that goes, there are only certain combinations of poles and slots that will work, and the determination of those can be very tedious. Many engineers just copy what's been done by others rather than completely understand how you determine that for your particular instance. There is a famous book written on this subject. It was originally in German back in the early part of the last century, entitled Motor Windings or something like that. And the author is a very famous professor from the University of Berlin. Lucius Gehrig was his name. And he's a man with two last names. I believe his first name was Michael. Lucius Gehrig, back in the 30s, he took on his wife's name, maiden name, as well as his. And when he immigrated to America and taught at Brooklyn Polytech, he translated this book into English, and it is available. And so he lists all the winding possibilities that there are, and the formulas and the methods to determine them, and lists diagrams of them in this book. It's a shame that American patent examiners don't have access to this book, because the U.S. Patent Office has issued a number of patents on winding and pole combinations that are covered by the principles in that book, which would make them not unique inventions, but the prior art's well documented in that book. But if you use multiple three-phase circuits in a stator, then that further limits your choices of slot windings for given slot and pole combinations. The ideal winding distribution factor is unity, and we're going to talk more about that. To utilize all the conductors in the machine, we should strive for as high a winding distribution factor as possible, and we'll study more about that in a moment. Let's summarize some slot to pole selection guidelines, and this applies to all three of these machines. As we said before, higher pole numbers yield higher torque densities and higher power densities to some degree, but the easiest way to increase the power density is to double the speed. If you double the speed of a motor, you've doubled the power density, because power is torque times speed. But some of the issues relating what happens when you change the number of poles. Well, if you double the number of poles, the yoke or the back iron is cut in half. Now, so what that means is, if you use less steel if you use a thinner cross section in the yoke of a stator, there's a couple things you could do with that. You can make you keep the stator OD the same, and make the slot depth the same in the stator, and make the rotor larger. Or your other choice is whatever you reduce the thickness of the yoke by increasing the number of poles, you take that off of the OD, and so you make the OD of the motor smaller. It depends which is the most important. You're going to get the same flux. The flux you get is independent of the number of poles, and a lot of people fail to realize that. But remember that's absolute truth. That assuming no leakage, there is a caveat in that statement, in that the higher the number of poles, the higher the leakage from the leakage reactance goes up with increased number of poles. But other than that problem, you don't gain anything by increasing, or lose it much by changing the number of poles, other than you need less steel, you need less yoke in the machine. So one of the things that we must remember, that when you're playing around with the number of poles, you have to deal with the effects of the change in frequency. And if you double the number of poles, you double the commutation frequency. Now we're going to study this later, but it's pretty well accepted amongst inverter designers that to produce a decent sine wave, they need about 20 PWM chops per sine wave cycle, so that if they're limited on the PWM frequency due to the losses that are acceptable in the IGBT bridge, then this can have something to do with the decision of how many poles you pick. For example, if I'm designing a machine in my consulting, one of the first things that I have to ask is, whoever's going to do the inverter, someone's going to design one from scratch, or they're going to purchase a standard one, what's the maximum number of poles they can stand with whatever PWM frequency they're allowed to use for transistor losses. So so the PWM frequency has a lot to do with the number of poles as well. The Stator slot selection guidelines, first of all, as we said, you want the highest winding factor. So if possible, integral slot windings give you the highest winding factor. If the number of if the slots per pole per phase is a whole number with no remainder after you divide the phases and the number of poles out, then you have unity distribution factor. Now, fractional slot windings lead to short end windings. That can be a big benefit. And fractional slot stators are very automation friendly. That's another important consideration, and is low cost to make. Multiple slot coil spans, which are required for integral slot windings, that requires very expensive insertion equipment. It's standard induction equipment. There's a lot of it around, but if you're starting out with a new motor design, you don't have that equipment. Why then these integral slot winding with multiple tooth coil spans, you either have to hand insert the coils, which is labor intensive, or you have to use very expensive automation equipment. Now, for induction motors, and reluctant synchronous and PM, there's a few factors that are different from one machine to the other. The comments made before aren't universally applicable to all these machines. They are applicable to the PM machine, but the induction machine and the reluctant synchronous machine, the issues related to the number of poles with those machines, it follows the same guidelines. It's been pretty well proven that for any induction motor that has an output of under 1,300 Newton meters, that a 4-pole is a very good choice, because if you go to higher poles than that, the efficiency and power factor drops considerably because of the leakage reactance and the synchronous reactance, and all the reactances are affected by higher pole numbers as the machine, in smaller machines. So the same thing applies to reluctant synchronous machines. Here's a nice slide that was developed by Professor Sung from a university in Australia, and he shows here what you can do with changing the rotor diameter. This first example here shows different values of the slot depth ratio. This is what you can do. You keep the stator OD is kept the same in all three of these. The stator OD is kept the same, but the rotor diameter has gotten bigger, so that the ratio of the slot depth has changed. So that's one variation in that you can consider when comparing and optimizing your design. This other one here is probably more important. Here we have the case of keeping the rotor diameter the same and changing the number of poles, and we've kept the slot depth the same. And you can see how with a 2-pole machine, the stator's this diameter. Changing that to 4-pole, the stator yoke's cut in half. Changing to 8 yoke, the stator is cut in half again. So the 8-pole machine has much higher torque density than the 2-pole machine. And consequently, you can look at this, and a coil for a 2-pole machine is going to have to be wound from here to here, all the way. So you got this huge amount of copper in the end turns, which makes the end turns long. With a 4-pole machine, the coil is wound 90 degrees. It goes from here to here, so there's much less. There's really the same amount of copper there's the same cross section of copper, but the strands are longer. So I'll say it the other way: as you increase the number of poles, the cross section of copper is the same into the paper, but since the length is longer, you require more end turn extension out the ends. it goes down with 4-pole, and an 8-pole, it only spans 45 degrees. The coils are real short, you see. This is a picture of a summary chart that was done by this guy that worked for Reliance Electric a number of years ago. Reliance was considering the future of their business, and so they did a technical analysis of their existing line of induction machines and how they might apply these for use with inverters. Remember, all their historical machines, as was the case with every motor company, was designed for grid power, constant frequency and voltage. But to use these machines for inverters, where you could vary the frequency and the voltage, how does that affect the number of poles? So they did this big study and concluded that the number of poles was optimized at 4 for machines of 1,000 foot-pounds or under. And if you go to 6-pole machines, you can you're very limited as to the torque rating of those motors. Really what it boils down to, it has a lot to do with the cord length on the surface of the rotor. You can use higher pole motors if the rotor's bigger. For real large motors, you can have high pole count induction motors, but not for smaller ones that would be under 1,000 foot-pounds. But if you go up to 10,000 foot-pounds, you can use 6-pole motors, or even higher, 6 or 8-pole motors between 1,000 foot-pounds and 10,000 foot-pounds. And that has to do with the fact that on those larger torque motors, the rotor is going to be bigger, so the cord length is bigger. It's a matter of the leakage, the percentage of the pole flux, as how much of that percent leaks to the next pole, leakage reactance. So for PM and PM brushless, whether they're DC 6-step or whether they're AC driven, if your speed, it's all based on speed. If the motor's going to go 100,000 RPM or higher, or frankly anything higher than 50,000 RPM, you have to use a 2-pole machine, because it's just the frequencies are just too high for the inverter. And of course that would be true. This is true for induction motor too, or reluctant synchronous motor, high speed ones. You have to go to 2-pole. But with the PM machines, you can go up to 50,000 RPM with 4 poles. You can go up to 25,000 RPM to 10 to 8 or 10 poles, and 12 poles or higher would be low speed under 1,000 RPM for applications such as torquers. And just to summarize the advantages of increasing the number of poles on a PM machine, you get a reduction in the active material cross sections, including the soft iron, the stator cores, the iron cores, and the magnet thickness is reduced with the number of poles. So that saves money, doesn't it? Higher pole numbers reduces magnet costs. We see it right there. Rotor diameter can be larger with the same stator diameter. Stator diameter can be smaller with the same rotor. Reduction of phase resistance improves efficiency and results in shorter end turns. But the disadvantages of higher pole numbers is the flux leakage. Pole flux leakage varies directly with the pole pair number. Iron losses increase with higher pole pair numbers, and higher PWM frequencies are required, which affects the inverter. Here's an example of the end turn resistance versus the number of poles. You could see that the percent of the stator resistance in terms of the percent of the end turn resistance as a percentage of the total phase resistances. You can see how that is, it's quite high for a 2-pole machine. It's half to 75% of the total resistance of the phase windings are in the end turns. That means that all that copper is eating up voltage. It's creating heat, but it's not producing torque. The only parts of the conductors in the phase winding that produce torque are the ones that are down the slots that link with the flux from the rotor. And as you could see, that percentage drops to 40 to 55% for an 8-pole motor. The RSM switch, the synchronous reluctant synchronous machines, my best advice is to start with an existing standard 4-pole induction motor stator. And many of the pros and cons that relate to PM machines apply to the RSM as well. The most important aspect of an RS machine is the design of the rotor, and the goal is to get as high inductance ratio as possible between the D axis and the Q axis as it lines with the stator phase windings. So that means that you have to create flux barriers and leave some flux carriers in there and have the proportions such that that you can get these inductance ratios over 5, 8 to 10 preferred, or higher if possible. And the maximum pole number that is allowed is similar to the induction motor, not because of leakage, but because of the ability to produce a high inductance ratio, so that you need a certain arc, or a length, a circumference arc between the L and D, or the Q and D axis, to be able to get a decent inductance ratio. Typical designs tend to have pole numbers equal to AC of the same, AC induction of the same capacity. First of all, the number of stator slots must be divisible evenly by the number of phases with no remainder. That's absolutely essential. And as we said, there's a limited list of slot and pole combinations. I'm going to provide you with a list. For each one of those combinations, there's frequently a multiple number of coil location possibilities, and each one results in a different winding distribution factor, and the most desirable and the maximum, of course, is 1. So you always want to select the winding or the coil location pattern for any given number of slots versus poles to give you the highest distribution factor. So what that means is, in terms of since the number of stator slots has to be divisible the number of phases, for 3-phase motors your choices are 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and so on. And since the phase windings must be balanced, all the slots should be filled with the same number of conductors, or you should have the turns per slot, or conductors per slot, the same. When I say conductors, I mean conductors of each side of the number of turns of a coil. I'm not talking about parallel. You want to have all the slots full of copper just for ohmic losses. But when I say conductors, I mean conductors is number of turns times 2. Conductors equals number of turns times 2. And so each phase, for a 3-phase motor, the coils have to be distributed 120 electrical degrees apart. So a fractional slot winding usually has the coils spanning a single tooth, or maybe 2 teeth, or maybe even more. Fractional slot winding can even have a coil spanning more than 2 teeth. You might have cases where one pole has 1 coil per pole per phase, and another pole might have 2 coils for that pole. But that 2-coil pole has to be 120 degrees apart for every phase for it to be balanced. A case of that would be a 4-pole 15-slot motor. as opposed to a 4-pole 12-slot motor. 4-pole 12-slot motor is an integral slot winding. A 4-pole 15-slot motor is a fractional slot winding by definition. But you can still have a balanced winding as long as each phase is unbalanced in and of itself. But as long as you have the unbalance of each phase balanced around the circumference of the stator, and they're in 120 degrees apart in case of 3-phase, 90 degrees apart in case of 4-phase, then you still wind up with a balanced winding. The symbol for number slots is used S in the United States and Q in Europe, just for your edification. Now, here's an ISBN book here that lists all the possible slot and pole combinations for different number of pole phases, and that's provided in Chapter 3. But based on a few simple rules of slot and pole choices that cannot provide balanced windings are provided on the next slide. The number of stator slots must be divisible by the number of phases, which we said with no remainder. And for the number of phases, to have balanced windings, the phases, the sets of phase coils must be spaced around the stator according to this. We already said that the 3-phase has to be spaced 120 degrees apart, while 2-phase is 180, 4-phase is 90, 5-phase 72, 6-phase 60. So here's rather than give you a list of possible winding patterns, here's a list of the impossible winding patterns. In other words, these you can't have 6 slots and 6 poles. You can't have 12 slots and 6 poles. These are the ones that aren't possible. I gave you a reference of a book that gives you the ones that are. So any slot and pole combination you come up with, you look it up in this list. If it's here, it won't work. Now, for induction motor, the rotor bar selection number is a totally different topic. It's a totally different subject because it's true that the current flowing in the rotor bars determine the poles that are induced in the rotor. That's true. So I guess you could say that for a 4-pole motor, the minimum number of bars in a 4-pole motor would be 4 bars, but you would never design a machine like that because you'd have too much current in each one of those bars. So you have a lot of bars provide the current flow that produces each pole, so that and different motor design experts down through the years have come up with sets of rules on how to pick the number of bars with respect to the number of stator slots. But most of these rules were all determined from experience of trying to start induction motors at a fixed frequency and voltage off the grid. That's where all those rules came from. And they're particularly stringent and difficult for single-phase motors because some combinations are just terrible and it won't work. The motor won't even start with certain bar combinations. But that whole subject, that whole topic tends to be mitigated and go away, as it were, if you could control frequency and voltage separately. So it's not so important. But a good guideline in 2 4-pole machines, I think a lot of inverter motor design experts would agree that the bar numbers should be 80% of the stator slots, or 8 or more poles, the bar number should be 120% of the stator slots. For higher pole numbers, you need more bars. That's a well-known, that's a rule you should mark down. And then, of course, never have the exact same bar numbers as you have stator slots. Never, never, never. My guideline, what I use, is somewhere between 5 and 7 bars per pole. Because if you look at the end of a rotor, for all the north poles, the current is flowing, by definition. Let's say it flows into the diagram, into the paper, into the drawing, and all the south poles, the current flows out of the drawing. Well, so the current flow of those bars produces the flux that produces the poles in the rotor. But the rotor poles aren't glued there. They're slipping, so that the specific bars that have the current going in one direction versus the ones going the other direction is changing right at the pole transitions, right at the plus and minus current transitions. So they're changing all the time. So the current is actually reversing in one bar between the two poles all the time as it rotates in accordance with the slip. So you want a sufficient number of current carrying conductors in parallel there between that to properly define a pole and make sure it looks sinusoidal. That's the only way I know to explain it, to give you a feel for why a high number of a reasonable number of bars is required. Now, with respect to NEMA frame motors, standard stuff have been built for years, and this is a chart that's provided by either Reliance or Baldor, but they're all the same company now, and they're owned by ABB. But here's a list of NEMA AC induction motors that were all originally designed for grid power, and you'll notice that they're listed by horsepower and number of poles, and then the stator, slot, and rotor bar number combinations listed there for your information. Notice that some of these are high efficient and premium efficiency motors. So as efficiency went up, they changed some of these. Not all of them, but some of them. You can study those. It's interesting. So the induction motors that are grid powered have their own set of rules. I list them here. I don't think they have a lot to do with inverter driven motors, but there's another list of rules that's given by Dr. Cyril Vienot in his priceless book, The Theory and Design of Small Induction Motors. It's a very famous set of rules. His friend Phil Trickey, had his set of rules either. And some of these rules are such that they, if you follow one rule, you violate another. That's what. But that's all related to grid motors, and you don't have to worry about it so much with inverter-driven motors. My guideline is to use 5 to 7 bars per pole for grid motors. I think it's simple. That concludes this lecture. Thank you very much.